Okay, this is the Unit 3. We're starting linear functions. We're going to focus in on different aspects of linear functions. So today we're going to look at graphing linear functions, and there's some vocabulary that we need to know for the entire unit. First is continuous functions. These are functions that we've talked about whose values are continuous or unbroken. Basically, you can trace the function from its beginning point, wherever that might be, all the way to its ending point without lifting your pencil. Discrete function are functions whose values are distinct and separate and not connected. Values are not continuous, so discrete functions are defined by their domain, and so that would be one where you see a bunch of dots on the screen, and you would obviously be picking up your pencil every time you wanted to go to the next one. So here's an example of a continuous function. Its domain is defined between -4 and +4. Inclusive because they are closed holes, so it'd be -4 less than or equal to x less than or equal to 4. Remember, if it's a closed hole, it's an equal sign. If it's an open hole, then it would be a no equal sign. Discrete functions is going to have a list of the numbers where those x's, those dots are at. So the domain here would be at -4, -3, -2, 0, 2, and 4. Domain is the set of input values for the dependent variable, that's the x-axis, over which the function is defined. So all the x values are in the domain. The range is set of output values for the dependent variable over which the function is defined. So we define that as either y, or now we can call them f of x values. Inequality notation is notation in which the solution is represented by an inequality statement. Here's a couple ways to help you remember what goes together. So if it is less than or equal to or greater than or equal to, you should see a solid dot. And now that we're working on lines, you'll see a solid line. If it's less than or greater than, you'll see an open hole. And now that we're working with lines, you'll see a dotted line. So we have our two faces to help us remember which ones go together. Parent functions is a set of basic functions from which related functions are derived by transformations. So there are three that we are going to deal with this school year. The first one is a linear function. It is f of x equals x or y equals x. And we would see the table would be all of the x's and y's would be identical all the way down. And we would see a line that's going in the positive slope, so positive up. And constantly increasing. A quadratic function is y equals x squared or f of x equals x squared, and in that case each one of our x's would be multiplied times itself and give you a positive answer. So -2 squared would be -2 times -2, which is +4. -1 times -1 is +1. 0 squared is 0, 1 squared is 1, 2 squared is 4. The domain for both of these are going to be all real numbers, but for a line, it will continue in both directions, all real numbers. The only reason these would change is if we'd see a physical dot on or open hole on the graph. Same thing with quadratic. We would have all real numbers on the quadratic, but our range would start at +0 or at 0 and go up positive, so y is greater than or equal to 0. Excuse me. The last one that we're going to have is an exponential, and this one looks kind of like a slide. Exponential is a whole number raised to the value of x. So 2 to the x, 3 to the x, 4 to the x, whatever you're talking about, okay? So I've done a couple of examples. So 2 to the -2 actually ends up giving 1/4. 2 to the -1 gives us 1/2. 2 to the 0 is always going to be 1. 2 to the first is 2. 2 to the second is 4. And then we would draw our graph. So we can denote it by y is equal to 2 to the x or f of x is equal to 2 to the x. The domain is all real numbers as long as it's the parent function. And there is an asymptote, that's the yellow dotted line here, at y is equal to 0. And so that makes our range y is greater than 0, not equal to. Linear equation in two variables is a relationship with a constant rate of change or slope represented by a graph that forms a straight line. So there are three forms of equations that we have for a line. Slope-intercept form, which is y equals mx plus b. It's the most useful one because it tells us our slope and it tells us our y-intercept. Point-slope form is used if you have a second point other than the origin. another point to put in, and you know your slope, so you can put this in, solve for y, and then it comes back to becoming a y equals mx plus b. In this case, you do not know what your y-intercept is. And then the standard form, which is the one that's most unuseful, is ax plus by equals c. And in that case, you would, for our calculator purposes, you'll always have to rewrite this one into by changing your using the a, b, and c to figure out what your m and your b is, so that you can then put it into your calculator. Okay, linear inequality in two variables is a relationship with a constant rate of change or slope represented by a solution set denoted by the graph of a line that may or may not be included, because it may be dotted, it may not be included in the solution, and the set of points above or below the line. So here's several examples. We have, technically the line is y equals x plus 1. That's going to be the same all the way around, but you notice the difference. Because this has a line here, this line is solid on both these two. It has a little line underneath the inequality sign. And then you, if you use 0, 0 to test, you can say 0 is greater than or equal to 0 plus 1. Is 0 bigger than 1? No, that means that the center cannot be shaded, so everything above the line has to be shaded. Here, 0 is less than 1. That means the center has to be shaded, so everything below the line. If it does not have that little line under it, so this little line is not here or here, that means that my drawn line has to be a dotted line. And again, we use the same process. Is 0 greater than 1? Nope, so the center cannot be shaded. Is 0 less than 1? Yes, so the center has to be shaded. Okay, linear function is a relationship with a constant rate of change or slope represented by a graph that forms a straight line in which each element of the input, x, is paired with exactly one element of the output, y. So again, we use the same form functions, but we do have to rewrite one of them. So f of x equals mx plus b, that is the same as the slope-intercept form. This is the rewritten point-slope form, m times x minus h plus k. We just rewrote it so that basically y was by itself, and that changed it to f of x. The one that's different is this one right here. This is the rewritten standard form in a form that can then be used in our calculator. And this negative a over b is actually a way of writing m, and c over b is a way of writing the y-intercept. Okay, slope of a line is the steepness of the line, and it has a lot of other names. It's also known as rate of change, in which you look at the vertical, the y, and compare it to the changes in the x, or the horizontal. It's also known as rise over run, or change in the y values or over change of the x's, or delta y over delta x. Delta means change. That's the funny triangle. AKA, it could be in the form of the slope formula, which is y minus k over x minus h. I changed the formula from what you see on your charts. Instead of saying y minus y over x minus x, I never like that. I always like h and k, because when you hit upper level math, we use h and k anyways. And also, you get a distinction between your xy, your first point, and your hk, your second point. Okay, it could also be known as m equals negative a over b, and that is used when you have the standard form of the line, where you know what your a, your b, and your c is. So that gives you a formula to find m. And it could be m if you see either of the equations, either the slope-intercept form or the point-slope form, and that is the slope. It's also known as the rate of change, and in any word problem, it's either going to be per or each. So wherever you see the word per or each, you're immediately seeing what the slope is. Ways that we can look at it is rise over run. If it's rise up, run over, up and over to your right, always run to the right if you can, okay? That will be a positive slope. If for some reason you cannot run to the right because it goes off your page, you can also reverse both of those. You have to reverse both, which means go down and go to the left. So we'd see either up and to the right or down and to the left to get positive slope. Negative slope is going to be a falling first, then running to the right, or arising first and running to the left. So it's the exact opposite to positive. And then we have two specials. We have the horizontal line, which is denoted as y equals something, and that one has a slope of 0. Or we have the vertical line, which is x equals something, and it has no slope at all. Because if you tried to do the vertical slope, it would be dividing by 0. Okay, last two things we want to look at is the intercepts. We have the x-intercept, which is the x-coordinate of a point at which the relation crosses the x-axis, meaning the y-coordinate equals 0. And we denote it as x is x comma 0, whatever the x value is, comma 0. It also has a couple of names. X-intercepts are also called zeros. Those are the values of x such that the y value of the relation equals 0. It's also called roots, mostly when you're dealing with quadratics. And that is the x value of the function graph where the function equals 0. And again, f of x equals 0, and you get the 2 points, x comma 0. And then we have a couple of a little shortcut to help us. When we have the standard form, we can find the x-intercept by taking the c value and dividing by the a value. And that will give us our x-intercept. The y-intercept is the y-coordinate of a point at which the relation crosses the y-axis, meaning the x-coordinate this time is equal to 0. We do 0 comma y. It also has multiple names. We call it b in the y equals mx plus b form, which is the y-intercept. We also have a b where we can do take the a and b, or a, b, c out of the standard form, pull off the b and the c, and c divided by that b is equal to the y-intercept b. I know that gets confusing. So here's what they would look like on various graphs. We would have the x-intercept is crossing the x-axis, the y-intercept is crossing the y-axis, and we denote it by negative 2.5 is 0 and 0, 2. And then we can see that on a table also. The x-intercept would have a number here of whatever it was and 0 in the y. And the y-intercept would be 0 here in the x equals 0, y equals whatever number. Okay, if it was on a quadratic, you would have two x-intercepts, or possibly one, or possibly none. Again, they're also known as zeros or roots, so you could have any of those words being talked about, and they're just talking about what's crossing the x-axis. I mean, that's literally all they're talking about. And then we would look for the same thing. You look for the 0 in the y if you're talking about zeros or x-intercepts. You look for the 0 in the x if you're looking for the y-intercept. Okay, so on my wall I have this chart, and I want you to use the chart to fill in the boxes. So recreate this particular reference chart on in your graph paper, and then look at the chart and make sure that you have labeled everything where it needs to be. Okay? And then finally we're going to do 4 examples. So the first question is talking about 2x minus 3y equals 5. Now using our calculator will not write it in like this. So we need a couple of choices. Well, the first thing we can do is figure out our x and y intercept. And the easiest way to do that is, let's say we want to do the x-intercept. Well, x-intercept means we're looking for the x comma 0. So that means we can set 0 in for y and then solve for x. So we're going to do 2x minus 3 times 0 equals 5. So 2x equals 5, because that becomes 0, right? Divide by 2, and we end up with x is 5 over 2, which is 2.5. Okay, so at positive 2.5, we have an x-intercept. Okay, then for the y-intercept, we're going to do the exact opposite. We're going to set 0 to x and solve for y. So we'll do 2 times 0 minus 3y equals 5. That becomes 0, so negative 3y equals 5. And then divide by negative 3, divide by negative 3. So y is negative 5/3, which is basically negative 1 2/3. Okay, so at the y of negative 1 2/3, which is right about there, we have our y-intercept. Now what I want you to do is now with your partner, I want you to discuss what do you notice about the x-intercept and the y-intercept in terms of the A, B, and C. So this is the A, B, and another color, C. Do you notice anything about those that was a result of how we got our x-intercept and our y-intercept here? Okay? And then once we have those two, we can actually use any kind of thing to connect our dots, but not just connect them. We also need to pass through them. That's really important. I think a lot of people make a mistake of not trying to pass through. So you want to start below it and go up above and below. So again, one of the things that I want you to do is draw the graph and then label it. So that's my x-intercept. This is my y-intercept. And then finally we want to figure out our slope. So what is the when you're moving left to right, from here to here is going up by 1 2/3 or 1.67. Okay? And then going from that spot to the next where they came here, this is 2.5. So if we want to find our slope, we would do rise 1.67 over run 2.5, and then using a calculator or just doing it by hand, you could figure out what your answer is. So real quick, I'm going to use my actual fractions instead, or yeah, I'll just do that. 1.67 divided by 2.5, and we get 0.668, which is basically 2/3. We'll just round to 2/3. So our M is positive 2/3. And I want you to do one more thing is look at your slope and look at the numbers A, B, and C and see if you can figure out how 2/3 was the result using the A, B, and C. Okay, our next example, I want you to do number 2 on your own. Again, using your A, B, and C, and using the idea that the x-intercept is x comma 0 and the y-intercept is 0 comma y. All right, so on problem 2, instead of using the concept of x comma 0 and y comma 0 comma y, I use the formulas for x-intercept, y-intercept, and slope, which is the M. The x-intercept formula is C over A, which is 1 is C and A is 5, so 1 over 5. Y-intercept is C over B, so C is 1, B is negative 2, negative 1/2. And our slope can be found by negative A over B. So A was 5, so negative A is negative 5, and then B is negative 2, so over negative 2, which is 5 over 2. Then with a little bit of editing, because I kept messing up, we can label our axes with any increment we want. So I decided to go ahead and label the increment at half. So each box is worth a half, mostly because my y-intercept was at negative 1/2. So if I do my negative 1/2 and then count up 5 and then over 2, up 1, 2, 3, 4, 5 over 2, I got a second point that was really clean point. And when I connected that point to my y-intercept, I actually ended up with getting the 1/5 where it needed to be. Okay, so those two ways that you can find your slope, your graph, even if you have a slope standard form. You can find your two intercepts. That will give you 2 points to connect, and then using those you can figure out your slope. Or you can use the little tricks, the formulas for x-intercept, y-intercept, and slope, and then use a combination thereof. So either the x-intercept, the y-intercept and the slope, the x-intercept and the slope, or whichever ones work the best. Now the last two things to look at is a horizontal and a vertical line. So a horizontal line, it is denoted by y equals a number, and that number is where it's crossing the y axes. So this one would be between 4 and 6 because I labeled my lines by 2's. And then it has an all real numbers for domain, but it's range is only 5 because it said y was only 5. Our vertical line is not a function because it doesn't pass the vertical line test, and it crosses through the x-axis at that number. So x is 2, it crosses through at x equals 2, has a domain of only 2, and a range of all real numbers, which is why it's not a vertical function.